Hi, welcome to Beginning Engineers. Today I'm going to be talking about quantum computing, a computing revolution. So I wanted to make this video because I've seen tons of videos on YouTube and other sites about quantum computers, and they always sound very fascinating, and it really seems insane what is coming. But I think a lot of those videos kind of breeze by why the technology works and what is so amazing about it. So the point of this video is going to really focus in on what superposition is and how quantum computers work, with a good example that hopefully helps you understand how significant it is. But don't worry, it won't be a physics course. I'm no physicist, and this is still beginning engineers, so we'll keep it as simple as possible. First off, what is the quantum world? What does quantum even mean? Quantum mechanics, also known as quantum physics, quantum theory, wave mechanical model, matrix mechanics, is a fundamental theory in physics that examines the world of the incredibly small, super small. Classical physics, which Isaac Newton modeled much of, was the guiding theory in physics until very recently, the 1900s. Classical physics deals with most of the world we can see and experience, and it's not adequate for describing things incredibly small. Apples falling from trees, people jumping off cliffs, things you probably had problems to solve for in high school physics class, that is classical physics. It was the quantum revolution of the 1920s that paved the way for our modern understanding of quantum mechanics. So many physicists were involved with this revolution, and you probably recognize some of their names offhand and or had to learn some of their equations in school. Look at the list below. I'm not going to read all those names, but a few notable ones: Max Planck, Niels Bohr, Heisenberg, Albert Einstein himself, the list goes on. Classical physics and quantum mechanics are considered the two main branches of physics. Sometimes you'll see relativistic mechanics and quantum field theory being another two in some groupings, but really from a broad level, it's classical physics and quantum mechanics. And many physicists are seeking a unified theory of everything that brings these two worlds together, because right now they are still very separate in many ways. The idea and experiment that explains the oddness of the quantum world very well is the double slit experiment. This experiment helps explain something called wave-particle duality. Look at my two images on the right. The top one, you see a metal plate with a single slit and then a screen behind it, with a lit up section showing a pattern that matches the slit in the metal plate. In the bottom image, there is a screen with two lit up patterns, and in front of that screen is a metal plate with two slits. These patterns in the screen correspond to objects being shot through the slits in the metal plate. The objects being shot can only pass through the slit, the opening in the metal plate. Otherwise, the objects would hit the plate. So let's imagine that we have a device that shoots marbles. If you shoot it at a plate with a single slit, it's either going to hit the plate and bounce off, it being the marble that was shot, or it's going to pass through the slit and hit the screen behind the metal plate. And in this scenario, the screen lights up with a pattern when something hits it. So if this device is shooting many marbles at the plate with a single slit, we will eventually see that slit appear on the screen as a pattern because of all the marbles hitting the screen. Now let's switch out our metal plate and our screen to a metal plate with two slits and a fresh new screen. And now let's take our marble shooting device and have it oscillate slightly. So it moves back and forth like 20 degrees, still shooting marbles continuously. What would you expect from the marbles passing through or hitting the double slit plate? Well, you would expect two patterns to appear on the screen behind the metal plate, and each one would match one of the slits. This is pretty straightforward with marbles. But what if we switch to water? Let's imagine we have access to a wave pool, and we can put the screen on one end of the wave pool and put the metal plate in front of it. What happens when a wave hits the metal plate? Let's say the metal plate takes up the whole width of the wave pool. There's water on both sides of the plate, obviously, because there's a slit in the plate, but if a wave is coming, it can really only pass through the single slit. The wave would pass through the slit, and we would see a similar pattern on the screen that we saw with the marbles. A section of the screen that is more lit up because that is where the wave hit it, the still existing wave. Everywhere else, the wave died down. So even using waves, a single slit plate pretty much is the same, whether it's a wave of water coming through or marbles. But what happens with our waves when we have a double slit plate? This is where things change. If a wave was released and came up against a metal plate that had two slits, that means two sections of the wave would make it through. But because waves spread out, they wouldn't just go in a straight line and make two patterns on the screen. The waves would hit each other. They would interfere with each other. They would cause interference and cause many waves to appear, which means on the screen you would see multiple patterns that look like slits, with different levels of intensity. So this is great and all when comparing marbles being shot through a single or double slit versus a wave going through a single or double slit. But what about electrons, one of the fundamental particles of the universe? Well, even though it's super tiny, an electron is a little object. So, shooting it through a single slit, you would expect it to have a single pattern, as though you were shooting a little marble through a single slit. But what would you expect shooting an electron through two slits? Say you shoot one at a time every couple seconds. Well, if electrons are like little marbles, we would just expect two patterns on the screen. A single electron goes through one of the slits, or it hits the metal plate and bounces off. But when this actual experiment was done, the screen showed the interference wave pattern when electrons were being shot, even one at a time. This means the electron was not behaving like the marble. The electron was acting like a wave. A fundamental particle was behaving like a wave. How is that possible? The electron was in something called a superposition, where it was existing in multiple scenarios at once. It was hitting the metal plate and bouncing off. It was going through one of the slits. It was going through the other slit. It was acting like a wave because it was existing in multiple states at once. A superposition. To understand this better, the scientists wanted to observe one of the slits. When they set up machinery to observe the electron, suddenly the pattern on the screen was just the two-slit pattern. Observing the electrons made them act differently. The superposition that was creating the interference pattern was collapsed. Quantum physics does not like to be observed. This seems crazy, but this is the reality of quantum physics. Imagine if you left your house at 8 a.m. and for 1 hour you were simultaneously shopping at the grocery, taking your car in for repair, or doing chores in your front garden, all at the same time, until a friend of yours stopped by to see what you were doing. Then suddenly, it was like you were only ever doing one thing. That seems insane, and that's not how the macro world that we can see works, but this is how the world of quantum physics works. And this is the potential being harnessed for quantum computing. It's these superpositions that makes quantum computers so powerful. So really take a second to understand that. So many potentials all at once. That's quantum computing. To understand how quantum physics translates into quantum computers, we first have to understand the basics of how computers work. Not too much, but enough to understand how you go from a binary to quantum. So traditional computers operate on software, operating systems, applications that tell the hardware, the actual physical components of the machine, what to do. And a very rough generalization of software hierarchy is as follows. You have the graphical user interface, the GUI, the GUI. That's what the user controls. So when you are on a computer moving the cursor around, or you're clicking buttons in an application, you are interacting with the GUI. That collects information from you, your inputs, and gives them to back-end software, higher level software programs such as Python. Below your higher level languages, you have the language C, which is called the mother of all languages, the mother of all computer languages, that is. And C was very advanced and novel for its day, but is still also incredibly important today. Below C, you have something called assembly, which is any low-level language where there is a strong linkage between the software and the machine code instructions for the architecture of the computer processors. So while C is more technical than Python and other high-level languages, assembly is super technical. You're very much referring to how to move different pieces of information around at a very modular level that is very strongly related to how your computer functions. It's a machine language. And keep in mind, when I'm saying technical, that doesn't necessarily mean it's more difficult. It's just less similar to languages we speak. So in Python or other languages, you might say something like, if x in this list, then outcome equals this. In assembly, it would not be so straightforward. It would be a lot more mathematical and formulaic sounding, less like spoken language. Below assembly, we have binary, and this is represented with ones and zeros. 1 for on, 0 for off. So binary is what is used at the lowest level of data storage, and each 1 or 0 is called a binary digit, or a binary information digit, a bit for short. And a 1 represents a physical switch, something called a transistor, being on, and a 0 represents that transistor being off. In binary, you only have ones and zeros. It's what we call a base 2 system, meaning there are only 2 digits used in conveying information, whereas our current number system is a base 10 system. We have 10 digits to choose from. So in our current number system, you can go from 0 to 9 with a single digit. But in binary, you can only get to 1 with a single digit. You have 0, then you have 1. There is no unique symbol to represent 2. So already we need a second digit to convey the number 2. So 2 in binary is 1, 0, because again, we don't have the digit 2 in binary. We only have zeros and ones. So if you look at my image there on the right side of the screen, the bottom one, not the top one, you'll see a progression of binary counting versus our current number system counting. Notice how quickly you add an additional digit for binary, because you can only get to 1 in binary before you need 2 digits. So 2 is 1, 0. 3 is 1, 1, because the first one represents 2, just like 1, 0 would be 2, but then we're adding another 1 to it. This makes it 2 plus 1, so it's 3. To get to 4, we need another place, so now we have 3 digits, 1, 0, 0. 5 is 1, 0, 1, because it's the 4. The first one represents a 4, plus the 1 on the end. So you'll notice every time you add a digit, you're getting to a higher place in binary. So with a single digit, you can only get up to 2. But then with 2 digits, you can get up to 4. With 3 digits, you can get up to 8, and so on and so on. That's what the top image represents. See how there's 5 places on it? Well, if the first digit was there, that could go up to 16. So with 5 digits in binary, you can get up to 31. Every new digit increases the potential number you can get up to by 2 raised to the power of whatever that digit is, minus 1, because the first digit can only get up to 2 to the power of 0, which is 1. The second digit, 2 to the power of 1, so you can get up to 2. So you can see with a fifth digit, you can get up to 2 to the power of 4, which is 16. So if we had a sixth digit, we could get up to 2 to the power of 5, which is 32. And when I say you can get up to 32, I mean just for that digit. So the sixth one, the starting one, could represent 32 by itself. So then we could still add all ones behind it to add the 31 we see in the image. So with 6 digits, you could get up to 63. These binary digits translate into the physical hardware of the computer through digital circuits. And I have an example of one called a half adder on the bottom of this slide. So each binary digit, each bit, is represented by the path that A takes or the path that B takes. And those two bulkier looking objects on the circuit are known as gates. Gates specifically allow something to happen based on a certain set of conditions. They are logical gates. Logic gates. Let's go into more depth on the half adder circuit, which is now the image on the top right. There are only two digits, A and B, and there are two logic gates, a sum and a carry. Now those aren't the names of the gates, but those are essentially what the gates are doing. They are either summing the two digits or carrying the digit if we are going to the next place and a new digit is needed. So the top gate is called an exclusive OR, an XOR gate, which only gives an output of 1 if either input is 1. Not both inputs are 1, and not neither input is 1. Only one of them can be 1. It doesn't matter which one. If one of them is 1, then the output, the S, the sum, will be 1. Otherwise, the output will be 0. The sum will be 0. The bottom gate is an AND gate, which only gives an output of 1 if both A and B equals 1. If they are both 0, or only one of them is 1, then the output C, carry, will be 0. So, with these two gates working together in the circuit, you can have any combination of bit A and bit B being 1 or 0, and the two gates will give you the appropriate output. And in the middle of the slide, you can see every example. If both bits are 0, the output is 0. If only one bit is 0 and one bit is 1, the output is 1. That's because the sum gate will give you 1, but the carry gate will give you 0, because they're not both 1. If they're both 1, the sum gate will give you 0, because it only allows one of them to be 1. But the carry gate will give you 1. So that means we have a 1 being provided by the carry gate and a 0 being provided by the sum gate. So we have a 1 and 0, which represents 2. And if each bit is 1, adding them together would equal 2, which in binary is 1, 0. So you can imagine that the carry gate would come first, but if it's 0, it's not displayed. It's not taking up data. Whereas if it's 1, it is displayed, and suddenly our sum gate showing 0 is now the second digit in line. So 1, 0 is 2 in binary. If it seems confusing at first, really read the point on this slide and look at all the different examples, and walk through each example, checking what each gate would do, and then look at your output. This is how binary converts to hardware in the real world. Bits becoming on or off signals. Millions of these, different types of gates, different types of logic setups. This is what allows software to run. And I went so in depth on this because understanding this allows us to go to quantum and see why quantum is so much more powerful. In the world of quantum computing, you have something called the qubit. It is the quantum bit. So in our last super in-depth example, we had 2 bits that could be in 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. But if you wanted to represent all 4 of those combinations at once, you would need 8 bits, because each combination takes 2 bits. But with quantum computers, 2 qubits can exist in all 4 of those states, all 4 of those combinations, at the same time. I emphasize this point so much because we've gone from needing 8 traditional bits to only 2 qubits. And this is because of that superposition we talked about earlier. So remember the electron existing in all possible states at once, making the wave interference pattern? That is what 2 qubits can do as well, but for calculations in digital circuits. And what really makes this amazing is that this ability, this superposition, scales with quantum computing. Every new qubit you add exponentially increases your ability for calculations. An example that you see a lot for qubits is that they can be both 1 and 0 at the same time. Because of that superposition, much like a coin that is spinning, it's not one side or the other. It's kind of like both sides at the same time. So, because computers are complex machines that do millions and billions of calculations using bits, this ability to exponentially do more calculations with far fewer bits is what makes quantum computing so potentially amazing. A computer that can properly use 64 qubits, so 64 qubit quantum computer, could model 18.446 quintillion states. And if you collapse the superposition correctly, you could go through 18 quintillion combinations to get your right answer. So just for reference, if you've heard of a terabyte, which is a trillion bytes, that is the 744 in the number listed. So you can get that many potential states out of 64 qubits. But handling that many qubits is not easy. To get even a few qubits to provide answers is very difficult, and quantum computing is still very much in the early days. Think about where regular computing was in the 1960s. Computers that did very simple calculations that our phones can do today took up an entire room and would take hours for simple calculations. In order for future quantum computers to be viable as well, the error rate needs to be reduced further. So because of these superpositions and all these possible states, sometimes we collapse the quantum state and get an answer that is wrong. And that seems crazy because current computers have basically zero error rates. It's super negligible, like 1 in a trillion chance a bit will be wrong and give you the wrong answer. And even once we solve these issues, many experts think that quantum computers will not be used for things that traditional computers are used for today, or at least will use them for very specific things we don't often do. So for example, you can simulate more advanced chemistry, like molecular bonds, very well with quantum computers. You can perform super fast searches of very large and complex databases. You can factor very large numbers quickly, and you can use it to break encryptions. So a lot of countries are very interested in quantum computing for this ability to break encryptions. Thank you so much for watching this video on quantum computing. This was one of my longer videos because this is a subject that I was very interested in, and I wanted to give a video that really explained how revolutionary quantum computing is. If you like this video, feel free to subscribe and give it a thumbs up. Have a great day.